Okay, Jay, Bismillah Rahman Rahim. Today we'll be discussing chapter 5, and this is the final chapter of paper 2. Basically, agenda revolves around discussing the different uh, steps involved in your software development lifecycle. If you are following a development model, what are the options you have there? What are the merits and demerits of each model? And then eventually we'll be more focusing on your structure charts, how to draw them, what do they mean, and if at some point you are required to convert between a structured chart and its equivalent pseudocode, how to carry about that. Once we're done with that, our focus will be on the finite state machines, what they mean, how to draw one, how to interpret one, what is the difference between finite state machine and a mealy machine. And then eventually we'll be looking at the different types of errors, testing methods, and test data. And finally, we'll be looking at how a process or a program is launched into the market by the different methods of your black box, alpha testing, beta testing, so on and so forth. So without further ado, let's begin with this chapter. Okay, the chapter starts off with studying the program development lifecycle. So basically what we understand about the program development lifecycle, or in other terms, it's known as the software development lifecycle. In simple terms, it's the term allocated to all the activities that take place when creating a software from its initial requirements all the way down to its final maintenance phase. And by maintenance phase being the final phase, it means the software was created, made live or deployed on the site, and then eventually brought into use. Okay, now then, so all activities that take place between these two states are part of your software development lifecycle. So there are many names and there may be sub parts of each part mentioned here, but our focus in this syllabus is with these phases. So analysis phase, design phase, coding, testing. Now, first of all, let's look at what it means by analysis phase. First of all, whenever you need to understand that we are in the business of problem solving. So when you are presented with the problem, it becomes our goal is to solve that problem using some software tool. But in order to successfully be able to do that, we need to first understand the problem clearly. So if you can define the problem precisely, the result, the ultimate outcome of defining a problem accurately is the requirement specification. Now, the requirement specification, in a sense, it is a binding agreement between the client from whom you're creating the software and the software house themselves, who will be providing the services. Once a requirement specification document has been drawn up and both parties have agreed on upon these requirements, we can move towards the planning and possibly thinking up of a solution. Now, there can be more than one solutions, and we have to decide on which is the most appropriate solution. Okay, when we are addressed with the problem, we have two approaches. We can go with the bottom-up approach or the top-down approach. The bottom-up approach means we start off with a sub-problem. We're using the most basic of requirements, because often whenever a client approaches us, sometimes the complete set of requirements are not clear right away. So we have to start off with the requirements that we are clear with and start working on with adding requirements with each iteration. We'll be looking at the iterative model in a bit, but in a sense, that's what's happening. So this bottom-up approach basically means that I start off with part of the problem, part of the solution, and then later iterations will basically have more features or added features to this basic solution. And eventually at some point, I will have the complete working model. On the other hand, the top-down approach means that I look at the problem in a bird's eye view without any details. But when I start, performing, refinement, that means I'm creating sub-problems of this giant problem. And these sub-problems eventually translate into their own subroutines, whether they are functions or procedures. But whatever it is, we'll have to draw up how this problem is supposed to be implemented in an algorithm. And as we studied before, we can represent an algorithm using your pseudocode, flowcharts, and the stepwise refinement approach specifying the sub-problems of a larger problem can be represented using the structure charts. We'll be discussing this in a bit. After we're done with the analysis phase and we are ready to start solving the problem, we have analyzed the problem and we have realized that we can solve it. We have worked up a plan, a timeline, estimated budget, and we're trying to now work on a solution. Now, what solution do we have in mind? How do you design the solution in detail? Do we need an identifier? What identifiers will it use? Am I looking for any arrays? Do I need a one-dimensional or two-dimensional array? Am I storing the data in hard disk, in text file or binary file, whatever it is? These are all questions that I need to be clear of before attempting the design phase, because this basically outlines how my data is being saved, what type of data I'm using, and if there's data translation between different parts of the solution, it's probably discussed over here. Once my design is implemented using flowchart and pseudocode, by the way, these algorithm drawing methods basically outline your overall solution. So if you can perfect this, if you can make this error clear, the coding part becomes easier, because code is what? Coding is what? The implementation is also known as the implementation phase. What is this? It is basically creating these algorithms or recreating these algorithms in some high level language so that I can actually have a working solution on my computer. So if I have created a perfect design based on my requirements, I can move towards implementing that in a high level language. And that is known as your coding phase. And of course, what language are we going to be choosing from? Depends on a lot of factors. What's more easily available? For what licenses do I have? What expertise do I have? What platform is that program supposed to be running on? These are all deciding factors of what language I should be using. After the language is done, while I'm programming the code or my coders are working on it, they will frequently have to change the code because they may encounter different errors. These errors can be syntax and they can be logic errors as well. But whatever it is, you will rewrite the code, try to undefine the error, rewrite the code. Maybe you will find another error, correct that as well. And eventually, at some point after multiple tries, you will end up hopefully with a completely working solution. Now, once you have a working solution, now we have to test it. We have to test it we have different methods for testing it, but eventually what agenda of testing is to try to find out if there are any errors here, if there is any problems. Obviously, logic errors are not all clear before testing carries out, because when testing is carried out, it's very good at highlighting any logical errors. What logical errors are, we'll be discussing that in a bit. But these testing phases are very important, especially if you want to provide your users with an error-free code. So the testing will highlight any errors if they have been left out unintentionally. So you can carry your tests. If, say, for example, your tests don't reveal an error, that doesn't necessarily mean that there are no errors. It just means that you're not testing it properly. So you being able to uncover errors using testing method is actually a good approach. It's a good thing, not a bad thing. Okay, essentially, as the term states, program development cycle or software development life cycle, basically what it means that it's a cycle. So basically some activities will be happening recurringly or happening repeatedly, and all activities will happen in relation to other activities. Design activity has to be carried out after analysis. Coding can be only carried out after design. Testing can only be done if there's a working program that happens after testing. And testing, after testing, I'm satisfied, customer is satisfied, you make that program live, you make it run on the customer side, it's under its full burden, foot pressure is now in full use. And if you encounter some errors or change of requirements, you will go towards maintenance. Okay, the first approach towards applying these models, the software development lifecycle, the first possibility of implementing the software development lifecycle is known as the waterfall model. Now, basically, as you can see here, all of the activities are mapped out over here. The overall diagram represents one fact here, that if I, for example, move from the design phase, I have to first of all carry out the analysis phase. Similarly, if I'm carrying out the coding phase, that means I must have completed with the design phase. Testing phase is dependent on the coding phase, and maintenance cannot be carried out after testing is done. So it seems like everything has to be carried out in steps, and that's exactly what it is. And the reason it's called waterfall is that I carry out steps, and it flows like water down a waterfall. Now, ironically speaking, unlike waterfall, we're not necessarily allowed to go back, because we have to move into the next stages. So to be successfully applying the waterfall model, our direction should always be forward only. If, say, for example, there's something wrong in this phase, I will have to go back to this phase to identify the problem. If I'm capable of identifying it here, then that's good. Otherwise, maybe it's the error somewhere here. So basically, I may have to step back a few steps, few phases, just to identify the error. Most probably, will find the error in the previous phase. But the thing is, the way waterfalls work, water flows in only one direction. So for a waterfall model, our progress should also be in one direction. So just to successfully implement waterfall model, at each stage, I should be satisfied that this stage is complete and there are no possible mistakes. Only then I progress to the next stage. So that's how a good waterfall model is implemented, that I am making sure that each stage is complete and there is no further work that can be possibly done at that stage. Only then I progress towards. So there is, yes, an essence of somewhat perfectionism in this. And yes, there is, but again, it has its own advantages and disadvantages. One of the few advantages is that it's actually simple to implement. Do one stage at a time. How straightforward is that? And each stage is very clearly defined. There's no confusion about it. And it is especially, this model is especially important if we have a small team to work with, which means that you have a handful of people and all of them will be all hands on deck at each phase. So basically you cannot assign any parallel work. So if you have a small team and everyone has to work together at each phase, waterfall model is the best way to go about it. Okay, so if, say, for example, if you look at the disadvantages, one of the leading disadvantages is that I don't have anything to show to my client until very late, at, say, possibly at the testing phase. So before the testing phase, I'm carrying out analysis, design, and coding. In fact, the bulk of my software development lifecycle using waterfall model, I'm doing work without involving my client. And naturally, the client who may have paid in advance money or may have paid the complete amount beforehand will get frustrated because they don't see any outcome of their requirements. On the other hand, the remaining two models we're about to discuss does not do this. In fact, they present their clients very early on in the stages with some working solution, giving the clients some feedback and that their work is being worked on right now and it's being prioritized. Even though I will be prioritizing in the waterfall model either, but I've got nothing to show my client. My client is interested in the working software. The working software only occurs after the coding phase. So it's not a good model for long projects, time-consuming big projects. It's the best model for small projects and small teams. And within stages, the progress is slightly difficult to manage. You may end up spending too much time at a particular stage, and this will cause, of course, the waterfall effect, causing the whole project being delayed. And since integration is done at the very end, if I have developed different modules, each module is implemented using the waterfall model. I do integration at the very end, which means that if there were any errors in all this time that were uncovered, it means those errors will remain uncovered and they may have very catastrophic effects. So these are one of the advantages of your waterfall model and disadvantages. So just to summarize, waterfall model, all stages of your software development lifecycle are laid out in such a way that each stage is dependent on the completion of the previous stage. If say I encounter some mistake in a current stage, I'll have to go all the way back to the previous stage to try to identify that problem and solve it. It is a good model in the sense that it's simple, easy to use, it's straightforward, do one thing at a time. It works best with small software houses and small projects. For long ongoing projects and big projects, this is not a good model. And then apart from that, each stage is clearly defined. And secondly, you progress towards this next stage only when you're clearly satisfied with the first stage. So thereby, in the long run, it prevents a lot of mistakes and errors. However, on the drawback, the waterfall model is that it does not involve that much customer feedback, the client feedback. And even if you did want to give any feedback, you're not able to do it until the very end, near the end of the whole SDLC, because of which my client may end up becoming frustrated or not being able to monitor their progress. Similarly, another disadvantage is that it is not a good approach. This waterfall model is not a good approach for long and ongoing projects. Now, what do you mean by ongoing projects? Projects whose requirements is bound to change frequently, because waterfall model does not take changes in requirements lightly. Changes in requirements cause that I go back on the way to analysis stage and possibly have to perform all the activities again. So my requirements has to be crystal clear and changes are not easily implemented in waterfall model. Now let's look at the next model, iterative model. Now, as mentioned before, the iterative model is basically what your bottom-up approach looks like. So basically, your client approaches you, and there's a great chance your client does not fully understand the complete set of requirements that they are expecting. In simple terms, your client doesn't know what they don't know. So they just simply come up to you with the most basic requirements of the problems they are facing and the software solution they are looking for. Using those very basic requirements, you create a working model. Because of that, my client is given instant feedback of their progress, of their work, of their requests, their commissioned work. And in the same time, they are also capable of giving feedback to that initial iteration. That feedback will be the basis of further requirements to be added to this new iteration, creating another iteration. You do this iteratively, adding requirements with each presented model, each presented solution, resulting after eventually you have run enough iterations, you will have end up with a complete working solution that has all the requirements that are expected from the software. And in a sense, you can say even the client is in a way discovering what they want from the software. And initially they didn't know, they had a few handful of requirements in their mind. They started working with those, presented the client with a working solution. And then you figure out, okay, maybe this should be also part of the software. This should also be added. And there you go, another requirement. The second iteration will also have this requirement. And you go back to your client showing the second iteration and said, you know what? I think this should also be part of it. And another requirement comes in. And eventually you have multiple iterations having each one having more requirements than the previous one. And finally, you will have a complete working model. Secondly, we have the rapid application development model. This model does, okay, by the way, I forgot. Iterative model advantages is that you are capable of prioritizing high risk and easy to implement tasks first, and you can start working from there. Each increment results in a working model. So it's a very good approach if you're thinking about impressing your client. they will instantly feel that their work is being valued, and they will say that yes, my client instantly provided with me a working model that I can evaluate and give him positive feedback, and this positive feedback will lead to further requirements. It is better suited for large mission critical projects. Now, what is a mission critical project? Mission critical means a mission critical project is such a project that will cause, which will pose as a huge risk financially or otherwise to a mission if it fails. So any mission critical software should not fail in any other circumstance, because if it does, it's going to incur huge losses. Okay, finally, drawbacks include that since I am working on repeated increments and working on repeated versions of the same software, each one having more features than the previous one, there's a great chance that I will be ending up using more resources. And of course, it does. Finally, each requirement, uh, each increment each increment, it results in more requirements. So that means, unlike waterfall model in which I have the complete set of requirements beforehand, here I don't know what I'm working with. Later requirements may cause conflicts in the current requirements, so you can't be really sure of what to expect later on. On the other hand, waterfall model has a very complete list of the requirements, and there is a great idea of what is to be expected. Now let's come to the rapid application model. The principle of rapid application model is that essentially your code is your solution is divided into modules, and each module is working separately in parallel. Each module has its own short iterative development life cycles, and each module is created iteratively, and each iteration has an added feature for that module only. When I have all of these modules created, I can integrate them into a complete working solution. And of course, integration at an earlier stage and results in a lot of problems solved. It results in quick initial reviews, encourage customer feedback. In fact, it involves the customer. It's good. It's a good thing because the customer knows what work is being carried out, and it's also a bad thing because the customer may not always be available. If you're depending on the customer's arrival, you will end up waiting as well, and these waits may cause devastating effects to your overall software development lifecycle timeline. One of the drawbacks is that systems that cannot be modularized, for which I cannot create modules, cannot reap the benefits of rapid application development. Rapid application development works with systems that can be modularized, and each module can be worked on separately and integrated later on. But if it cannot be modularized altogether, it's not going to be a good approach. Secondly, since this is a code that may cause a lot of errors because you're working on multiple iterations, you will also require highly skilled developers and designers that attempt to create a working model error-free at each iteration, thereby reducing the chances of creating further iteration or possibly finding errors in those iterations. And then we have the structures, the different designing, program design and structure charts, different representations that a program can be represented. Let's try to understand what a structure chart is. Basically, if you understand what stepwise refinement is, and if you don't, let's consider this diagram. And for the time being, ignore these arrows and the text beneath them. I will ignore this arrow and number 2. I will ignore this arrow and number 1, number 2, number 1, average. All of these arrows are omitted. Ignore for the time being. When you ignore all of these arrows, the remaining diagram that you end up with is a stepwise refinement diagram. Now, if you add the working of parameters within these subroutines, then you will end up with your structure chart. Now, basically, you need to understand what these symbols are. This symbol means data transfer. And okay, first of all, what do these rectangles mean? The rectangle on the very top represents the program, and these are all the sub-programs that are run in this main program. So off the top, I can see that this structured chart basically highlights which program is my main program, and which programs are my subprograms. So as you can see here, all programs have this rectangular shape. So this is all, these are also programs, but they are actually part of the main program. Second thing that we see from this structure chart is that it represents the arrow of, or it represents the sequences, the sequence that is followed when implementing these subroutines. So by that logic, this subroutine is executed first, this is next, followed by this one. So going from left to right, the leftmost element is supposed to be executed first. So after that, another disadvantage or another, another feature of your structure chart, one, we discussed the, what you call it, details. We saw that this outlines the subroutines. Second thing is it outlines what subroutines are being occurring or occurring first, what comes next, so on and so forth. So another thing it highlights is the hierarchy. Hierarchy means that these are subroutines and they're actually called within this parent routine, if you must. So this subroutine is calling these this main program is calling these subroutines. So it basically represents the hierarchy that goes into this overall program. Now, if you look at this statement here, this structure chart, this is the structure chart that was used to represent our pyramid drawing program that we studied in paper 2. And basically what we're doing is that we're creating a pyramid using a particular symbol, and it just draws that pyramid. And basically this is the structure chart for that algorithm. As you can notice here, that this pyramid has these subroutines, including this one over here, that it's calling, first of all. Secondly, it also sees, you also see this arrow, this arrow coming back to the top. This arrow basically represents what subroutine are running in a loop. So as you can see here, this arrow touches this line, this arrow touches this line, and this arrow touches this line. So that means is that these arrows are now severed. These arrows, these links are not, these, basically what that means is that these subroutines are repeated. These subroutines are being repeated inside a loop. So basically this represents a loop right here. This is a loop. So if, say, for example, output spaces, output symbols, and adjust values for next row, these subroutines are part of a loop and they will be executed in this exact same order. This is the condition that will determine how many times this loop will run. So a second thing I can see here is that there is a loop that can be represented in the structure chart. First thing we saw is what are the subroutines of the main program. Second thing we saw, the hierarchy, what is the main program and what program is calling the main subprograms. Third, we saw the order of the subroutines, starting from left to right. This subroutine executes first. In fact, amongst this is the first subroutine to be executed. Anyway, left side, then this, then this, then this. Then we saw that this loop can be used to present if there is any subroutines that is being executed again and again. In this case, this subroutine is these three subroutines in exact same order, output spaces, output symbols, and let's just adjust values for next row, are executed in a loop, and the loop will run as long as this condition is not true. Apart from that, we can also do a third thing. We can also represent the decision. Now, basically what this means is that I can choose between two different paths, two different subroutines. So for example, let's just say if I have this decision table here, if the winner is found true, then I will run this, for example. If not, then I will run this. So basically it means that I can choose between two or three subroutines or two subroutines based on the decision program. So if I want all of them to be executed, then I don't need to mention this because they both will be executed from left to right. If I want a loop on subroutines, then I can use this method. And if I want, say, a decision to take place between two subroutines, only one should be executed, I will use this symbol here. So this is basically your important aspects of your structure chart. Now let's see what these arrows mean. These arrows, this is known as data coupling. Basically what this means is that this subroutine has resulted in the generation of these values. It looks like these values are being returned, but these values are generated because of this subroutine. This value is generated because of this subroutine, and you can say that it's being returned. Finally, if your arrow is coming back, it means that these values will be used as a parameter in this subroutine. These values will be used as a parameter as well. This double-ended arrow represents updation. So basically what that means is that number of symbols is being passed here as a variable, and in this subroutine somewhere number of symbols will be updated and returned back. Same thing goes with number of spaces. So this is data movement. Hollow circle arrow is data movement. And if it's coming up, that means this subroutine is generating these values. If it's coming down, that means this subroutine using this value as a parameter. And we have double-ended arrows, that means data is being updated. There's one more thing that's not mentioned here, and that's a flag. What does the flag mean? Let me see. Yes, let's just say, for example, this is flag right here. How do we know there's a flag? For example, look at the arrow. The arrow is not hollow, it's actually filled, black hole. So basically flag means what? It means it's true or false. So basically if my subroutine is simply expected to return true or false, that's what it will do, because it will return a true or false or Boolean value over here. So these are just few tips that I need you to understand about structure charts. Now let's look at how we will, in fact, in the next video, we'll be discussing how a structure chart can be interpreted or maybe even created based on the requirements presented in the form of either plain English or a pseudocode. Okay, so one of the benefits of working with structure chart is that with a structure chart, you can get a good idea of what the function header will look like. Now, of course, this is just stating names of subroutines. Their exact code inside is not mentioned here in the structure chart. So then there's no way of guessing what's the exact set of statements being executed in this subroutine or this subroutine, what's for that matter. So we don't know that yet, but you will be required at some point to possibly create function headers based on a structure chart given, right? So let's check out the one possible representation of this structure chart with respect to its function headers. Okay, so as you can see here, this is my main parameter program. It has the subroutines used initialize values, output spaces, output symbols, adjust values for next row, and there's another subroutine input maximum. So let's try to create a function header based on these translation of data for each of these subroutines. Again, in this structure chart, there's no mention of what's happening inside the individual subroutine, so we don't have to worry about mentioning that here. Our concern is to create a very perfect or appropriate function or subroutine header for these subroutines. So let's look at the first one, input max number symbols, which is returning max number symbols. Okay, so function input max number symbols has been defined. As you can see here, there's no data coming into this subroutine, so there is no requirement of any parameters. And in my definition, there are no parameters here. There are no parameters here. Okay, after that we have a subroutine by initialize values. Now initialize values does something and it returns these 4 values. Now you must be noticing that I have not used this as a function, even though it's putting out 4 values. The thing here is that pseudocode, the techniques you studied so far in pseudocode, do not allow you to send multiple return values. You can return one value and mention the type of data you're returning, that's it. But you cannot return multiple values at the same time. Python can do it very easily, but we have not come across an example where that's happening here. So in that case, what we can do is that since returning multiple types of data is not possible, what we can do is that we can simply assign that as a procedure because it's not returning anything. So I will simply call initialize values and it assigns them these initial values, including causing this subroutine to run as well. Moving on, let's see output spaces. Output spaces, from the looks of it, requires a parameter. And that's why, and since it's not returning anything, it will not be considered as a function. So in that case, output spaces takes number of spaces as a parameter and the type of which is integer. And it doesn't return anything, so I don't have to mention return or call it a function. Similarly, output symbols right here takes two values as a parameter, number of symbols and symbol. We go like this, number of spaces is integer and symbol which you're passing is type character. Finally, we see a double-ended arrow here. Basically, double-ended arrow points towards your updation. And for updation, our parameter passing takes place using byref. So if I'm not mentioning byref, it means it's byval for sure. So all of these are byval, byval, byval. But when I'm returning specifically something of integer Boolean type, I will mention that. So adjust values for next row is type is by reference because I'm assigning a value to the function. I'm sending a value to as a parameter to the function or to the procedure. That procedure is changing the contents of this value and possibly returning it back. So where do we see that happen? In a say a by reference function. It happens only in by reference function. And that's why adjust values for next row causes number of symbols and number of spies to be passed, but they have to be both by ref so that any changes in this subroutine, any changes in these values will basically mean that whatever variables are pointing towards the same memory location, changes are reflected in all of those variables. So in the next lecture, we'll be looking at how to draw or possibly interpret structured chart. So we'll be right back.